This lecture, we're going to talk about failure criterion and how those get used when we do, material, assessing whether a material will fail under a particular load or not. So, as a sort of a start-off example here, what I have is this simple connection where we've got two steel plates which are getting pulled apart, and then we have a steel bolt which is also getting pulled apart. And then I've highlighted here in red really this plane on the bolt, which is both getting sheared and pulled in tension. So in previous portions of this course, we talked about, well, we can compare a tension load to a tension stress or a shear load to a shear stress, but really, how do we deal with these combined loadings? And this is a relatively simple connection and simple relatively straightforward loading condition where we just have some shear and some tension. But how do we deal with multiple of these forces? And know, well, will this area here be okay? Will it have enough capacity to sustain load? And what we do is we use Moore's circle because if you remember, Moore's circle is, well, we can take a plot here in our sigma and tau space. Well, we can take a given stress state, and we can then transform that stress state. So we'll do a little tiny drawing over here. So we can take that, and we can transform it to, say our principal axes for, looking only at tension, or we can look at our maximum shear stress. So that means, for a given stress state, well, we have an analytical tool with Moore's circle to compare it back to these other stress states. So how does that help us in determining failure? Well, in essence, what we can do is we can do simple material tests, and we can find, say, we can just simply pull on a material, or we can push on a material in one axis, and then we can take that stress state and relate it to a whole bunch of others, and that's really what we're doing with our failure criterion. Is we're relating a particular stress state to uniaxial tests. And why do we do uniaxial tests? Well, because they're easy to do. It's easy to just grab a piece of steel and pull on it straight. It's difficult to not only set up loading with multiple conditions, but then also measure what that response is. So that's a really brief overview of, what are the tools we're going to use. Let's just give, I'm going to sort of walk through a little bit of what the failure criterion are. And we're actually going to start sort of at the end by really just displaying them, and hopefully, and then we can walk through each one a little bit of how they're used. So, we compare a stress state with Moore's circle to known material properties. With failure criterion. So this says failure criterion instead of failure criteria. So, there's what we're looking at are not I guess maybe to rephrase it, if we want to find out whether something's going to fail under a particular load or not, there is no unifying theory which defines how a given material is going to break under a particular load. Instead, there are a series of these failure criterion which work better in different conditions and not so well in others. And those conditions are really broken down to whether the material is ductile or whether it is brittle. So I'm going to present 4. We're going to look at 3 of them, and you'll look at the next one actually next semester in your geomechanics course. So the 4 that we're going to talk about are ranking. And these are really named after who proposed them or popularized them. So we have ranking, which is also known as R max, normal stress, we have Tresca, also known as our max shear stress criterion. Then we have von Mies. That's our max distortion energy. And then we've got more Coulomb. And as I said, we'll talk about these 3. Now, as I said, some of these they're better suited to different types of material. And going with the theme of presenting them first, we'll also present where they work well first, and then talk a little bit more about how we use each one. So for ranking, these are really good for brittle materials. And so that would be like cast iron or ceramics. And then both Tresca and von Mies are good for ductile materials. So that'd be metals like steel or aluminium. And then more Coulomb is actually used quite a lot for soils. So for those who do geotechnical engineering, you actually do a lot of more Coulomb failure criteria. So, as I said, what we've looked at previously with our Mohr's circle, and how we're going to relate our Mohr's circle to these various criteria, or criterion, are we looked previous, and we either we were comparing a principal stress, which remember is just everything's either in tension or compression, no shear, or we looked at a max shear stress. And that's really how we're going to relate these. So what we would do is we would get a tension test. So the way we start is we get a determine material properties. And so the way that we determine these material properties, as I alluded to earlier, is we either do a uniaxial tension or compression test. So by uniaxial, it means we would just, so say for the tension test, we would just take this bar, so I'll just write tension here. We grab both ends and we pull it. And if I was to draw out the Mohr circle, really what we're going to do, we're going to pull it until it yields. And, well, if if we think about our stress state, well, we've got we only have stress in one direction, and it's really this sigma 1, and so our Mohr circle looks like sigma 1 here, and we're going to pull that until sigma 1 equals our yield. And you can think about, as you pull, you're going to get, essentially bigger and bigger Mohr circle and stress states until that increases. Similarly, too, if we have a material that we want to look at in compression, we're going to do the same thing, but we're just kind of going to push it until the material crushes. Some materials yield in compression, but many just tend to they'll either buckle first or they'll break and shatter. And similarly too, we've got this ever increasing Mohr circle until the material gives up, and that's going to look like that. So we do these tests, and I say we, I mean this is the collective profession will do these tests. So if you're using these failure criteria, what you do is you look up these material properties, sigma y or sigma ultimate, so the yield stress or the ultimate stress. And if we plot the stress strain curves for those, so say we have a ductile material, it will yield, and then it'll have some, say, strain hardening. And this is our classic stress strain curve for steel. And then I'll draw a brittle material over here. It doesn't have a real yield curve. It just pretty much comes up like a candy cane and breaks. And it will break at some sigma ultimate. We'll have some sigma y, and this will be some sigma ultimate. So if this is our ductile side, and this is our brittle side, conceptually what we're going to do is for these different failure criteria, we're going to compare the way that they're going to fail to a given yield stress. So for for one way we could do is we could compare tau max to sigma y, which is what we do for the Tresca. And keep in mind, because we've got Mohr circle, we have a way to compare our tau max to sigma y, and that's useful for us. Or we might compare our principal stresses, sigma 1, sigma 2, sigma 3, to sigma y, and compare all of them together, and that's really what we're doing in von Mies. And then for our brittle material, again, we'll be comparing our principal stresses, sigma 1, sigma 2, sigma 3, but instead of comparing to a yield, because we have a brittle material, we compare to the ultimate strength. And that's what we're doing in ranking. So that's conceptually, that's all that's going on with these failure criterion. We're taking a known material property, and we're comparing it to our stress state that we can pull off of Moore's circle. So what we'll do is we'll just walk through Rankine, Tresca, and von Mies, and see, well, how do we use these in practice? If this is conceptually what's going on, how do we actually apply these? So we'll start with Rankine. And Rankine is also known as our max normal stress. Criterion. As I said before, so these are really good for brittle materials. And because brittle materials, like I showed you here, they really don't yield. So we're going to compare it to the ultimate strength, because if there is no yield, this doesn't make any sense to try to compare it to a point of our material properties, which doesn't exist. And what we're going to do, I guess, if we are to update our failure criterion, we're going to focus really on plane stress conditions. So that's our sigma 3 equals 0. And that's really just a simplification for this course. You can use all of these in for non-plane stress. So if you have loads coming in on all principal axes, excuse me, but it becomes a little bit more complicated. And for an undergraduate course, there's still lots we can learn with plane stress. So for Rankine, that says that for plane stress, and remember plane stress, sigma 3 equals 0, if sigma 1 is less than our ultimate, as well as sigma 2 is less than ultimate, then no failure. So that seems like a pretty straightforward criterion. So how does that look like? Well, so say we draw our Moore's circle, and sigma tau, and it's saying that, well, if we compare, based upon our arbitrary stress state, if we compare sigma 1 and sigma 2, and if they're both smaller than say this this overall sigma ultimate, which could be either in tension or in compression, which is why we compare both sigma 1 and sigma 2, then we're okay. It says that we have our principal stresses haven't made it up this curve yet, and so no failure. So that's pretty easy. So how we yeah, it's just a really straightforward, simple equation. So what does that look like if we want to sort of get a more graphic overview of it? So say that we take our sigma 1 and our sigma 2, and let's plot it instead of this sigma in tau space. Let's plot in our sigma 1 and sigma 2 space. And what this does is provides us sort of a graphic overview of whether something is safe or not. And so for our criterion, it says, well, if sigma 1 is less than, the ultimate, and that could be, either positive or negative, because materials can fail in either tension or compression. So, this is our tension side, and this is our compression side. And remember, that's just from sign convention. We said tension's positive, compression's negative. And then our orthogonal principal axis can also fail at sigma ultimate, negative sigma ult, negative sigma ult. So if we plot that, and if we want to sort of plot this criterion graphically, what we get is a series of lines where, any sigma 1, as long as both sigma 1 and sigma 2 are less than our ultimate stress, and then if we just sort of shade that in just to show it, really, if we have any combination of these two, you can think about that as, plotting on a graph. So it could be here, could be here, could be here, could be here. Any of these two combinations, which is less than the ultimate stress for both, then we don't have any failure. So you can sort of consider that as sort of our safe zone. If we have either one of them, so say that we move this this dot over here. So say we increase our sigma 1 to something over. We have a sigma 2 stays the same, but sigma ult is over here. Well, that's good. Then this failure criterion tells us that we're going to get failure. So this is our unsafe out here. And this surface is what's called a failure locus. And it's really just a graphical way for us to look and see, if we want to look at a bunch of test data at once, this provides us a really nice way of doing it. In terms of determining whether, a given material is going to fail or not, you don't need this plot. You only need to be able to apply this formula. So that's it. That's ranking. It's actually, it's not that scary. It's pretty straightforward. So moving on from there, let's look at our next failure criterion, which is the Tresca criteria. So for Tresca, this can also be thought as the maximum shear stress. Criteria. And, when we first talked about materials, I said that brittle materials tend to fail in tension along principal axes, and that ductile materials tend to fail in shear for materials. And so, because ductile materials fail in shear stress, we want to compare tau max to sigma y. And as I said at the beginning of this lecture, we're comparing back to sigma y because to test something in pure shear and to measure that shear stress is quite challenging. However, being able to just pull on a bar in tension is relatively straightforward, and then we can use Mohr circle to determine, well, what was the maximum shear stress at that location for when the material yields. And so if we go back to our little tension test, and we plot the Mohr circle for that, so if we pull this until yield at sigma y, we have some tau max at yield. And we know that from Mohr's circle, well, tau max is the radius of this circle, so tau max is just going to equal sigma y divided by 2. And that means that, if tau max is less than sigma y divided by 2, then we have no failure. And again, it's a fairly straightforward criterion. So how do we use that in practice? Well, either we can build a Mohr circle, or often we can get finding principal axes tends to be a bit quicker and easier. So we can compare, and it's more convenient to compare normal stresses to normal stresses instead of shear stresses to a normal stress. So basically what we're going to do is compare diameters of Mohr circle as a proxy, and that it's equivalent, but it's sort of a more analytically convenient. And we compare those to sigma y, which is, for plane stress, that's the same as as the diameter of the Mohr circle. So for sigma 3 equals 0, well, let's draw one where we have our sigma 1 and our sigma 2 are the same sign. So say we've got our first Mohr circle. Sigma 2, sigma 1. And as we talked about in our 3D Mohr circle lecture, we have sigma 3, an orthogonal one over here, and then if we rotate about the sigma 2 axis, we have some tau max up here. But really, what we are more interested in is, well, what is our total diameter of this Moore circle, and compare it back to sigma y over here, this diameter here. And so if both sigma 1 and sigma 2 have the same sign, so they can both be in tension or both be in compression, then if sigma 1 is less than sigma y, no failure. If, say, that we had principal stresses with opposite signs, so say that one of the principal stresses is in tension and one is in compression. We'll draw that again. So say you've got a sigma 1 and a sigma 2. Well, sigma 3 is still, we're working in plane stress, so our other Moore circles about the other principal, rotating about the other principal axes, are in here. So if sigma 1 has different sign from sigma 2, then all we're going to do is we're going to compare. Again, this is really all going back to just comparing diameters of our failure criterion, because what we're really looking for is this tau max, and we're just going to compare the normal stresses as a nice convenient proxy, because it's mathematically equivalent, is less than sigma y, then we have no failure. And like I said, what we really care about, for the Tresca is what our max shear stress is, and comparing this max shear stress, making sure that it's less than half of our yield. But because Moore circle gives us this nice mathematical equivalency, we can do this same comparison simply by comparing the diameters of our Moore circle, and we can do that with here. So if we want to plot, so we plotted the sort of failure locus and for ranking. What does that look like for our Tresca? Well, so we'll do Tresca. So that failure locus looks something like this. So this is our sigma 2 axis and our sigma 1 axis. Because we're looking at a ductile material, we care about yield, negative sigma y, negative sigma y. And it says that, well, as long as our principal axes are, the combination of the two is less, then we won't have any failure, and that means that we end up with this hexagon for our sort of failure locus. And so if you've got a sigma 1 and 2, which are both less than yield, well, you'll be, this is in here is safe. However, if you have, say we have this same Moore circle, and we sigma 2 stays the same, and sigma 1 increases until we go out here, well, this is a failure. And just like with ranking, you don't need these plots in order to use these criteria, but they are a nice way to sort of visualize test data and see, if you've got a pass-fail. All right, so now we're going to look at our final failure criterion that we're going to use in this course, and this is called von Mies. And this is based on the maximum distortion energy. And again, this is for ductile materials. And so while the first two criteria are really quite straightforward to derive, this one's a bit trickier, because what it's saying is that if it's relating really the change in volume and what the strain energy is for that respective change in volume. So if we look just at principal stresses, sigma 2, sigma 1, sigma 3, so that's our total stress state. Well, it says that that's actually a combination of the average stress plus, and then if you subtract out the distortion energy. And by distortion, think of this as, again, kind of like shearing. So, you can distort we'll do it in 2D, you're distorting this rubber band here. So this is sigma av, sigma average, sigma average, plus, and this is going to be basically this minus this, sigma 2 minus sigma average, sigma 1 minus sigma average, and sigma 3 minus sigma average. So it says the total stress is going to equal the volume changing stress plus the distortion. Stress. And we can use the concept of strain energy to define this distortion stress. So, from strain energy, and we get this relatively complex equation, 1 plus Poisson's ratio divided by 6 times the Young's modulus, sigma 1 minus sigma 2 squared, plus sigma 2 minus sigma 3 squared, plus sigma 3 minus sigma 1 squared. And that's kind of that's kind of a nasty equation. But for plane stress, we actually get a nice simplification. Zero. Then if we do some, some math in there, what we end up with is sigma 1 squared minus sigma 1 times sigma 2 plus sigma 2 squared. If all of that's less than sigma y squared, then we get no failure. And if we take a look at that sort of equation, really what it does is it plots an ellipse. And so if I pull out your notes here, you'll see, well, this is our failure ellipse, and over top, on the dotted line, we've plotted the Tresca criterion. So you can see they're very similar. The Tresca is probably a bit more conservative than the von Mies. And the von Mies actually does a really good job of for ductile materials in terms of being able to match up with test data. Just like with the others, you find if you can find your principal stresses, and if they're all within this loci, it's safe. If they're outside, it's unsafe. And I just wanted to also highlight to say that these are real. So again, in your notes on page 742, this is the principal stresses of some actual test data compared to these failure criterion. So the box here is max normal stress. That's our ranking, and it's a little hard to see here, but there's this little cross symbol, and that's cast iron. You see, it actually lines up pretty well. For steel, it's the open circle, and you can kind of see it somewhere between the Tresca and the von Mies, and on down. So you can see the stuff. It does work in practice. And that's essentially it. So I've done just this small summary sheet to kind of boil down, all of the key components for each of these, and maybe we can zoom out a little bit, and so we can try to see the whole sheet at once. Where for our summary, where we've got ranking, it's useful for brittle materials, and we're comparing a failure and normal stress. So you need both of your principal axes to be less than your ultimate stress to be safe. For the Tresca, it's ductile material, and we're looking at comparing our max shear stress to a yield stress. So if the magnitude of your Mohr circle is less than yield, you're going to have no failure. And then for von Mies, it's distortion energy. And we can use the strain energy for a given volume change in order to derive that. And if basically it says that if your principal axes, if you plot this out and it's an ellipse which is smaller than the ellipse here at yield, then you have no failure. And that's it. So they're kind of a challenging thing when you first see them. They, failure criteria and these things must be really challenging. We've got these funky graphs. But really, in terms of utilizing them, it all goes back to this notion of, we have some unknown stress state. We want to develop a Mohr circle. And then we can, whether we've got a brittle material, which fails typically in tension, or in compression, or if we have a ductile material which tends to fail in shear, we just then compare back to test material, simple tests, so uniaxial tests, to known points on there, and then we can compare. Essentially, what we're doing is we're comparing these Mohr circles to these more circles with these criterion, and that's really all it is in practice. So with that wraps up our discussion on failure criterion, and thank you very much.